Hi, this is Mrs. Wiederhold. Welcome to my video on dilation and reflection of parent functions. Now let's get started. In general, when we think of the word dilation, it means to expand or to stretch. In mathematics, we can dilate a function two ways, vertically or horizontally. And today what we're going to be talking about are two types of vertical dilation. The first one is vertical stretch, and the second one is vertical compression or shrink. Let's talk about vertical stretch for just a moment. How I picture this is, I don't know if any of you remember silly putty or if you've ever played with that, but think about holding that silly putty at the top and the bottom, and then you pull on it lengthwise, and when it stretches you can just kind of see it get thinner and even narrower. And that is what happens with our parent functions. When there is a vertical stretch, it's as if they're being pulled lengthwise. They become narrower and even appear taller. Now let's talk about vertical compression or vertical shrink. Now this picture is a little different. Picture a poster board that you have rolled and you've carried around and it's all been rolled up. And then you want to unroll it, but it's really curvy. And so what would you do to get the curves out? You might take a big book or something big and you would lay it down on top of it until the board flattens out straight. And that's kind of like what vertical compression is. If you picture the quadratic parent function, that is kind of like a U, a right side up U. And when you compress it, vertically compress it, it's like it just lays open and is going to lay open flat and ultimately could be a horizontal line. I hope those images have helped picture what dilation can look like. Now let's talk about what it looks like in the equation. The number that represents the dilation is in front of the first term. This number is represented by the letter A. And if you'll notice, I have a couple of examples. My first example is of the quadratic parent function, and we've put the A in front of it, and so now we know there's going to be a dilation. That curve is either going to be narrower or wider than the parent function, depending on what that number is. And then my second example is for a parent radical function, putting the letter A in front of that. Again, if you look at that graph, it's going to be taller or it's going to be flatter. Now let's take a look and see exactly what the letter A can do specifically to your equation. Any number greater than 1 or less than -1 represents a vertical stretch. So let's look at some examples. 2x squared, 3x cubed, 4 times radical x. Those are all examples of a vertical stretch. And actually we could do something like this, 1.1x squared. 1.1 is greater than 1, so it also represents a vertical stretch. Now, the further away this number gets from 1, meaning is it going to be positive 7x squared or 2x squared? 7x squared would be more narrow than 2x squared. Now let's look at some negative examples. Negative 2x squared, negative 3x squared. All of these are examples that are numbers where the A value is less than -1 or greater than 1. Now what this would look like on a graph is if we said that this is the parent function and this represented y equals x squared. Now if I were to change this to y equals 4x squared, then my parabola, as it's called, would be narrower. Okay? And so now what we're going to look at next is what happens if we have an a value that's greater than 0 but less than 1. Any number between 0 and 1 or between 0 and -1 represents a vertical compression or vertical shrink. Those terms are used interchangeably. Now let's look at some examples. We could say 1/2 of x squared. We could say 1/2 of the square root of x. We could also say 1/3 of the absolute value of x. These are all examples of what the a value looks like if it's between 0 and 1. If it's between 0 and -1, it would look something like this. -1/2 x squared, -1/4 square root of x. Another example, we could say 3/4 of the absolute value of x. And I'm sorry, I meant to say negative. Now, what would this do to our graph? And again, I'm going to go back to the quadratic parent function. So we're going to say that graph looks something like that, and that's y equals x squared. So now if I want to say that I want to use negative, well, let's see, not negative yet, I'm sorry, 1/4 of x squared. And what that would do is that would flatten or make our parabola wider. Now we have talked about two types of dilations. We've talked about a vertical stretch and a vertical compression. Next, I want us to look at the reflection or reflection of our parent functions. A reflection is when the function is reflected or flipped over the x-axis. A negative sign at the beginning of the equation is used to represent a reflection. Now we have already seen what this looks like as an equation. Remember I showed you we could say -2x squared. So not only does this show a vertical stretch, but because of the negative sign, it shows that it's reflected over the x-axis. Let's do another one. We could say -4 times radical x. This also shows that the graph will be narrower, but because of the negative sign, it will also be flipped or reflected over the x-axis. We could also show, let's say, -2/3 of x squared. Now, this shows the 2/3, the fraction that's between 0 and 1, shows that this is going to be a vertical compression. But because of the negative sign, it also means that it is reflected or flipped over the x-axis. Now let's look at what this looks like graphically. I'm going to start out with our quadratic parent function, and it would look something like this. And this is y equals x squared. Now, if I were to write y equals -x squared, it would stay exactly the same shape. It's just that it would be flipped over the x-axis, if this is the x-axis right here, okay? That's what it means. It would be reflected or flipped over. Okay, now let's review. We talked about a vertical stretch, and that could be represented like 4 times x squared. Remember the 4, it's greater than 1, so it represents stretching vertically or making our graph narrower. And that would look something like this. If we had our parabola was like that, and that would be y equals x squared, okay? So now if we wanted to show that vertical stretch, it would look something like that. And it should have the same vertex. I know I'm not showing that very well, but it should. Okay? And vertical compression would have an A value that's between 0 and 1. And that could look something like this. We could say 1/3 of x squared. And graphically, it's like we are just trying to flatten out that parabola. So it would be wider. Again, it should have the same vertex. Now, a reflection on any of these, you would just have a negative sign in front of the A value. And that would look something like this graphically. For the parent function, it would literally just flip. It wouldn't change the width, even though mine's not drawn perfectly. It would not change the width. If I wanted to now draw negative 1/3 x squared, it would look something like this. And if I wanted to graph negative 4x squared, it would look something like this. Now I hope this video has helped you understand a little bit more about dilations and reflections of the parent functions. I look forward to working with you again. Bye-bye.